Thank you. And just kind of one kind of more question before we open up to the rest of the panelists we've had it today. What do you think? You focus on so many fantastic different areas and technologies: sensing, actuation, energy distribution. To you, where's the biggest fundamental improvement we need in technology? Is it in the fabrication, and is it in the complexity of manufacturing? What's the big open challenge from your perspective?
I think it's bottom-up assembly. That in order to do all these things, if we just had high surface area to volume control, better control over high surface area to volume structures and energy systems and sensing, we could do so much more. We have examples of liquid crystal elastomer actuators, which have high force densities, but can't really do much work. The reason is it's a small volume, and you can't get light into a large volume of liquid crystal elastomer. But nature would have designed some kind of vascular system of total internal reflection or something to get light in and distributed over the whole LCE. Our muscles are awash in glycogen that can be very high surface area to volume ratios to get the hundreds of thousands of fibrils to, power them locally. Yeah. Can't even get close to that, and that's why everybody's like, we don't have any good artificial muscles, and it's because we don't have high surface area to volume control like biology does, because it has self-assembly.
That's really interesting.
Maybe I can ask you another question along this line. So concerning this concept of embodied energy, right? We had a lot of discussion yesterday about embodiment as a meaningful constraints for optimization in biology or in the future of robotics. And energy is certainly playing a very important role in the evolutionary context, I think. Do you think the concept of embodied energy coming into picture of optimization of robot design or control optimization of soft robots and stuff like that, do you actually see in the same way, or do you have different views?
Yeah, I think that, so there's so many ways. I specifically described liquids as energy storage, and fluids as energy storage, methane gases and ionic liquids. But as that other diagram showed, there's many different pathways of converting energy into motion that could be embodied. And I worked with you specifically to come up with this phrasing of embodied energy, because I think that embodied intelligence, the paradigm you all have, is the right way to look at this with. Now, the science of it, I don't have that. We in our predictions in that graph that showed different energy density versus power density trade-offs, and this is just our imaginations. Like, we think you could do this, somebody should do this, but is this the right way to do it? We don't know. I think that the pedagogy and the philosophy that embodied intelligence has, when applied to embodied energy, will create order of magnitude effects on the endurance and agility of robots.
Yeah, and I also would like to ask the same question to Dan and Pietro here, because we're looking at the biological systems, and energy is a crucial thing, and in the context of locomotion, in particular, energy is a very crucial parameters, both in nature and in the engineering world. I don't know, Daniel, what do you think about your views on energy as a constraint of embodiment or optimization of control or design of the system?
I wish I could think of anything intelligent to say. I'm sorry, it's I haven't studied anything about energetics, physiology of organism movement. And I'm not an engineer building, state-of-the-art devices, so I probably better not comment on that. As excellent a question it is, as it is, I probably better not comment.
Yeah, I mean, the only thing I can add is that in microscopic systems, a huge amount of energy is devoted to movement. So when you look at bacteria or algae at single cell, they expend, when they are moving, they're expending about 80% of their energy in the movement, which is huge. But then they're also not necessarily completely optimized, because they need to perform different tasks with the same modules. So that it's very rare in biology to find something that is actually 100% optimized the way you would engineer it.
For that, that's a really interesting observation that I hadn't thought about. Like the scaling laws related to this, like small scale would require much higher energy per time or power, I guess. And then, but then maybe because is this right, that because they're so small, they're surrounded by more energy and it's easier for them to take up energy? Is that a
Yeah, and I think that's also true of, if we manage to engineer systems that exploit biology in that way, then energy will probably be fine, because kind of fixing carbon is something that is actually very efficient. So photosynthesis, and we could probably use ATP or whatever. And I don't think energy as a source will be a problem if our computation is working with that sort of biology circuits.
Yeah, Alex, I think that the historian you're talking about, Alexander, maybe his studies.
Well, there's certainly plenty of understanding of, metabolic activity and cost in scaling of that over organisms. That's for sure. And Alexander happens to have plots in his book. That has a long history in biomechanics, and but how that relates to design.
I'm actually surprised that Daniel didn't look at the energy aspect of this, because the thermodynamics is terrible in terms of energy efficiency, right? You lose a lot of energy just by interacting with all this dumping environment.
Well, it's interesting for me, and just as Pietro was saying that, it occurred to me, one of the things we've found, I guess, in the last number of years, and I alluded to this, is that a lot of the organisms we've been studying that are either, particularly when they're swimming and moving in complex materials like sand, but it could be grass like Chen Li's studies, it could be leaf litter, it could even be a centipede crawling over rocks, and there is a huge amount of dissipation relative to inertial forces. And from that point of view, I think that yes, the problem has been, for me, is that it's just hard to measure energetics in realistic environments. I mean, the classic studies of metabolism and oxygen consumption, whatever, are in relatively pristine versions of the world. You put an organism on a treadmill and you your oxygen consumption, and when you're starting if I want to understand how a lizard buries in sand or a cockroach scuttles through leaf litter, well, I just don't think folks have looked at that yet, and our technology may not be good enough to really resolve these kind of things. It's an interesting question, though, that Pietro's comment, and given that we have this now, at least mechanical connection, life at low Reynolds number is mechanically not so different than life in high friction number, whatever. It might be interesting to think about. Not everything, we tend to see large animals and robots bounding beautifully across flat landscapes, where indeed you can minimize, or using storage and return of energy, you can defer some metabolic cost, but I think at the smaller scales, it's interesting to think about for sure.
I was involved in a conversation about robotics a couple of years ago, where people were suggesting robots should be cold-blooded, in, I think, the idea that they would be somehow require less energy. But I have the opposite opinion, that I think we should be lots of highly dissipative systems, empowering them a lot, and warm-blooded, hot-blooded, nuclear-powered robots, possible. Eating themselves, autophagus systems. you know, there's a lot of space to play with in energy in robots.
Adam, I think thank you for joining. We finally have a chance to chat with you. Do you have anything to add in terms of embodied intelligence or embodied energy or computation, morphological computation? Do you want to give your views on this?
Yeah, thanks, Famia. So, yeah, apologies. I missed all of Famia's emails about this and completely missed the opportunity to speak at the workshop, so I appreciate that. And Rob has already messaged me to point out my pretentious telescope, so I acknowledge the elephant. It's not there on purpose, it's simply there. My daughter uses it to look at the stars. So,
Here it is.
this has been a great workshop. Thanks for this. I'm keen just maybe to have a panel discussion about application space, right? You know, this is, you know, for me in the engineering department, you know, sort of engineering of systems to perform tasks, to perform missions. You know, there's loads of discussion about, you know, fundamentals, work about science, work about sort of basic technologies. But I'm also interested in sort of maybe just soliciting the views of the assembled great and good here of where all this goes. What do you use it all for? Why is it interesting? What are the stakeholder held problems that these technologies can solve? I have my own views, but I'd be keen maybe just to have a wee chat about that before talking about embodied intelligence. Rob, why don't you go? I'm gonna point at you. Give us your thoughts.
Well, so in the case of these soft systems, they're finding use underwater because of buoyant support, on people because we have skeletons, and so I don't know if you've seen it, but there's a dielectric elastomer actuator powered swimmer that was swimming around at the Marianas Trench, just because of the simplicity of design, the distribution of electronics within solid volumes of elastomer is able to handle those crushing depths. In space, you can have large structures deployable with small weights. But on people, these are haptic interfaces, and I think it's a very, very important part of our future that we don't necessarily think about because it's hard to implement. So we have vision systems, and we can't see not having cameras, and we can't see not having, like, VR doesn't exist without VR goggles. But if we were able to access our nerves the way we can, our tactile sensation, where we can access our optic nerves, we think totally differently. Our brains have as much computational resources devoted to touch as they do vision. It's just harder to do technologically because of various things, like the large areas our mechanoreceptors are spread over, the difficult and changing topographies. But we can survive without vision. It's very hard to survive without touch. So I think haptics is a future that some of us, including me, initially disregarded, like as an art project, but it's not. It's a real science, and it's very hard.
Yeah, and in fact, can I just echo on that, Rob? Because, you know, one of the things we've been finding, among others, is that as you start to, again, I'll be from the terrestrial point of view, as you start to study organisms and robots and interesting pterodynamic interactions, it's all contact. You know, you can't avoid contact. This is particularly obvious in snakes, right, where the whole body becomes, you know, an actuator and a sensor at once. But and I think that's one of the lovely things about soft robotics, what it can bring to, you know, the paradigms in robotics is avoid the nastiness, avoid obstacles. But here you embrace them and use them, and without good touch sensing, good contact sensing, there's no chance.
Really, I completely agree with that. I mean, we had a paper that we put into ICRA a few years ago, which was in a session on avoiding collisions in robotics. And we put in a paper called "Embracing Collisions in Robotics," and it was basically about all of the information that you get when you smash robots into stuff, when you make robots bounce into walls, when you make them push against the environment.
Love to see that paper.
Derive all of that information from, and it's hugely interesting, hugely important stuff. So I think for me, a big opportunity in soft robotics and embodied intelligence work is about how you use all of that embodied intelligence, how you take that sensing, how you take that information, and basically use it to derive information from the environment. Change the paradigm of robots from moving through a space without touching anything to touching everything and getting the information out of it in that way. Because there's so much more than vision that you can get from robots.
And I think also, Adam, there's a great point. I'm just thinking of Pietro's stuff, you know, clearly there's room for that hydrodynamically too, right? I mean, there's probably, even in Stokes flows, I just like saying that because you're on the call, even in even at the micro scale, you know, there's probably enormous amount of information that one could sense. Maybe organisms aren't using it actively at those scales, but robots certainly could in the flow fields and structures. Certainly at higher Reynolds number, you know, I know moths, my colleague Simon Sponberg's been looking at how moths utilize vortices on their wings, they're shedding, but this seems like a really interesting and actionable
I completely agree. I don't know if Francesco's on the call or not, but Francesco's doing some great work in that space on exactly that sort of concept. It's really, really interesting stuff.
I think one of the things, that, for example, we have Animal, we have some Spot, we have some fantastic robots that really push the boundaries in that way, not just in terms of kind of the technology, but also manufacturing acceptance and such. Like, we need something like that for this community. We need something out there that we can say, yes, this is an example that we can make a difference in terms of application and in terms of society. I feel we collectively need to find what that problem is and what that looks like, such that we can really kind of try to make this kind of application-oriented impact in the way that we've seen in other areas of robotics.
We have examples of large-scale implementations of soft systems. They're just not whole-body soft robots. I brought it up a couple of days ago somewhere else, but like we have magnetorheological fluids tuning the damping of military vehicles autonomously, and you know, Herb Shea, they haven't commercialized, at least I don't think they've started selling yet, but they have Herb Shea's group has these really great haptic output devices that seem quite ready. Soft Robotics Incorporated is doing quite well. And then there's a spin-off company called Root AI that's working in agriculture and has very compliant grippers picking fruit. So these are all, agriculture seems to be a killer application for these things. Logistical operations in factories, underwater robots, haptics, probably space deployment structures. You know, there's a lot of things. What is missing is the reliable manufacturing of things. Like, you can't make things one-off. You need to make thousands and millions of them, and they all work the same. So that's, I think, the bottleneck.
Yeah, I agree with that, Rob. We're doing a lot of work in offshore energy. That's where we're getting a lot of traction. Things that will interface with wind turbines and tidal turbines and things like that. Because again, instead of worrying about avoiding collision, then you design systems that interface directly with the surfaces. But again, yeah, it speaks to exactly that point about manufacture. How do you make these things? You know, and yeah, making manufacturing great again.
Well, the additive manufacturing section I have is all about digital light synthesis, which is just projection lithography in 3 dimensions, and it is really good. The problem with it is not multi-material. So when you talk about 3D printers, many times they'll have multiple materials available. This is only one, but it is fast, it is high resolution, and it's not like beating your head against a wall. Usually what you print works. And especially if you printed it once, it works a second time. So it's like injection molding, but 100 times slower. But 100 times slower is probably okay when you're talking about robot scales. So it's a process we're kind of betting on. There's a new technology called volumetric additive manufacturing, which is like holographic, or not. It's like you materialize things in seconds. Anyway.
Rob, I wondered if we could discuss a little bit this theme that you spent some time on about the energy, And also, I guess Pietro was mentioning also the type of energy and power that's available for different size organisms. And I think when we look at large robots, I mean, one of the things about power, at least, I'm not sure about the energy yet, but you can imagine a lot of these new ones, Boston Dynamics with internal combustion engine, could also put a large fuel tank on them. So I think with a large fuel tank, you can probably store a whole lot of energy, maybe similar to Walrus. The question, I guess, though, is the power. And so I'm wondering, one thing is the scaling that I just posted in the chat, you know, this kind of curve about a lot of mammals and like at least warm-blooded organisms, how you can have more or less all the organism put on a straight power curve line. But I think with the internal combustion robots, we are already kind of at or way above, you know, in many of the cases above that curve. So it's not a question of power necessarily, but if we have to try to pinpoint and put our hand on something, what is it that differs between some things that are milder without moving parts, you know, something like the battery type of robots versus the ones that have internal combustion? One thing for sure, they're noisy. But is that a big problem? You know, so in some ways, maybe the robots are already doing better than a lot of things in the natural. But on the other hand, maybe we can try to classify several of these technologies and plot the several curves. Like maybe the internal combustion robots, let's plot them on a curve, you know, different sizes. How about the battery ones? And then maybe some other ones that are powered by different mechanisms. Then we have at least some insights on how far we can go. I think that kind of curve is very powerful.
I think you're right. And I didn't want to say man-made technologies aren't good compared to nature. In many ways, they're better, higher power densities, higher efficiencies on DC motors, and even, you know, turbine engines. But the degrees of freedom you have versus the energy densities, nature still wins. Like in these combustion powered, like Big Dog was initially combustion powered. Google didn't like it. They needed it to be quiet, but I agree, many applications you could be loud. But the degrees of freedom you have to operate with an internal combustion engine are pretty small, and where we have musculature everywhere. So I think if you combine, and that's one of the things I was thinking about with this embodied intelligence and embodied energy thing, is like you somehow have to have the energy consideration, but still the agility of and dexterity of animals.
I wonder if it's only dexterity. So I don't have the answer, but one of the things I was thinking as far as the embodied intelligence we were talking about, right? So one thing is just the raw power, and the other one is about like the computation. And at least in terms of computation, the human brain is really amazing. You know, there's nothing we can match yet in terms of, you know, cycles per unit power spent. And I think our brains are usually what, 20 watts or so. With 20 watts, it's really small computing that you can still do. So the question is like, is there something to be learned from this kind of scaling also, how much power is spent on movement, but also how much power is spent on computation, and how we do something about that connecting to the body?
I think it's a really interesting area of you know, discussion. I think a lot of this is about the fact that typically when people design robot systems as a whole, efficiency is an afterthought. It's not something which is looked at up front. And especially in lots of the soft robotic work that's been done, we design things which have a huge amount of hysteresis in them. So we do work against the compression of gas, we do work against the elastomer, and none of that is returned, right? So, you know, but I mean, we see this with all sorts of other robot systems as well, like Animal, for example. We do work in offshore energy with Animal. And for the most part, the best thing to do with Animal would be to chop its legs off and put wheels on it, because they're much more efficient. And so we find ourselves solving problems to do with getting robots to go up and down stairs, because scientifically it's interesting. But practically, you would just do what you do with vacuum cleaners at home. You have a Hoover upstairs and a Hoover downstairs, and you don't worry about it going up and down the stairs, because that's not the important task that it's solving, right? So I think a huge amount of effort in robotics is directed in the wrong way. And sometimes, you know, especially when you're considering things like efficiency, very, very few systems are designed explicitly with the goal of optimization of efficiency. There's usually other metrics that people are trying to optimize on. And when you do optimize on efficiency, then you can look for the major sources of dissipation. And huge sources of dissipation in all soft robotics is currently, to do with hysteresis in work done in pressurizing fluids and work done against elastomers. So if we were to change the paradigm in terms of thinking about how would we design a system to be as efficient as possible, that would have very different mechanisms, very different technologies that would implement. But also, one of the things that we're interested in my group is, regardless of the efficiency, regardless of the way in which the system dissipates, the other one, which is really, really important, which speaks to sensing, is about being able to do prognostics, being able to predict how much energy the system has left in order to be able to complete a given task. Because until you can get to that point, you can't actually use soft systems in anger, because you're working without any of that sort of predictive ability. So I think it's a really, really interesting discussion thinking about power and thinking about dissipation.
And I think that really nicely brings together this interdisciplinary aspect. We need to be careful what we're trying to optimize for and what we're trying to aim it at, and we really need to consider this whole kind of body kind of systems from robots. And I'd just like to thank you. I think that probably brings us to an end, unfortunately, for today, because we need to move on to the breakout sessions. But I'd really like to thank all our panel speakers and our guest speakers. Thank you, Adam, for a last-minute drop-in for the last session. It's been a really, really fantastic afternoon of talks and really interesting.
Can I just say, Adam, your telescope is pointing the wrong direction.
Josie, thank you. And Fumi, thank you for this. This has been a lot of fun and continues to be a lot of fun.
Thanks very much.
Thank you, everyone. Really, really interesting discussion. So really good afternoon. So just before we move on to the breakout sessions, just a few reminders. First of all, we start tomorrow at 9 a.m. GMT, not 8 a.m. So there's no breakout rooms tomorrow. Second, on Discord, we have some chat rooms that are available if people want to have a after work, like beverage or the alternative in a relaxed environment, and those will obviously stay open, so please feel free to make use of those.